I've included these pictures to show you how quadratics are really a part of your everyday life. Parabolas can be found in everything from roller coasters to cave formations. You'll be shocked now that you know about them and you're learning about them, how many you actually see in your environment. In this lesson, we're going to learn how to solve quadratic equations. Up till now, all we've done is graph them. So we need to go through some vocabulary before we begin. And the vocabulary words you see here are all somewhat related. They have words in front like mono, bi, and tri. These are words that you've dealt with before. Mono means one, bi means two, and tri means three. Nomial means terms, and so when we're talking about a monomial, we're really talking about a one-termed expression. And it can either be a number or a variable or the product of them both. A binomial is a two-termed expression, and it can be, or it's described as the sum of two monomials. And a trinomial is a three-termed expression, and it's the sum of three monomials. So I will give you a quick example of each. A monomial might be something like 2x. Okay, so that's a number and a letter, but they're being multiplied, so it's the product of a variable and a number. A binomial has two terms. Well, that might be 2x plus 4. And a trinomial would have three terms, and that might look like 9x squared plus 2x plus 4. Okay, so we're going to move on to FOIL now, and FOIL is something you do when you have two binomials and they're being multiplied together, and remember that's first, outer, inner, last. So FOIL is used when two binomials are being multiplied together. And then there's our final vocabulary word, which is factoring. And I'm going to underline that because it doesn't look like there's a vocabulary word here. But factoring is the undoing of FOIL. Where you take two binomials and multiply them together, you're using FOIL. Well, we're going to start with perhaps a trinomial and break them back into the two binomials that created that trinomial. That's called factoring. It's the undoing of FOIL. And sometimes you might want to think of it as division or dividing up a trinomial. But you can also factor things that aren't trinomials, like if they had a greatest common factor. And you've dealt with that before, where you had two terms and they had a common factor of, say, 2 within both of them, and you would factor out a 2. Well, that's what we're going to work with today. So I'm going to show you what I mean again about the undoing of FOIL. And so I start with this example here where we have two binomials being multiplied together. And if you were to use FOIL, you would take the first terms and multiply them. So x times x gets you x squared. The outer terms, x times 3, give you 3x. The inner terms, 5 times x, give you 5x. And the last terms give you 15 when you multiply them. And so then you would add together or combine your like terms to get 8x. And here you end up with your trinomial. Well, what we're going to do today is work it backwards. We're going to start with our trinomial, and we're going to break it into its two binomials. So I will give you a hint first, and you always start with that first term, usually if it's an x, and you know that it took two x's to get you that x squared, so I put those in. Then the next thing I think to myself is what two numbers when multiplied got you that 15 there? And you would find all those products that get you 15. And perhaps you know it already, and this is review, and if that's true, just move right ahead in this video. But two numbers that could get you 15 might be, 1 times 15, all right, and we also have 3 times 5, and you have the negative versions as well, but I'm going to leave those out right now. And so after we get our factors that give us 15, our question is which two of those factors add up to 8? And so you go back to the factors you've listed and you have 1 plus 15. Well, if I added those, and I shouldn't say equals, but if I did 1 plus 15, that gets me 16. That's not what I'm looking for. I'm looking for that 8x that's in the center, so what two factors got us there? But if I took 3 and added it to 5, then I get the 8. And so what that should be telling you is these two numbers, 3 and 5, were indeed our factors. And they were both positive, so I could write those in here as x plus 3 and x plus 5, which we already know are correct because that was our original problem. Well, let's practice this again with another example. So here we are with the trinomial x squared plus 7x plus 10, and I've tried to color coordinate it for you. And so I always like to start off, very first thing is putting my x's in the first positions of each binomial, because you know that you had to have an x and an x there in order to get x squared. Then I say to myself, which two numbers, when multiplied, give you 10, but when added, give you 7? You start off with the factors of 10, and you only have 1 times 10, and then you have 2 times 5. Those numbers multiply to give you 10. Well, which two of those, if they were added, would give you 7? And hopefully by now you see that it would not be 1 plus 10, that's 11, but 2 plus 5 gives you that 7. So I will use those as my factors and put them into the binomial. And so I know my one factor was x plus 2, and my other one was x plus 5. And this is another example where you should never get these wrong, because you can check these 100% of the time to make sure you're 100% correct. And so if I FOILed it, I would just make sure that I get this trinomial back out. So x times x is x squared, 2x plus that 5x will give you the 7x, and then the 2 times the 5 gives you a 10. So you've confirmed that your factors are correct, and the signs are correct too, which is important. All right, this next example is slightly different in that our middle term is a -8. And so we're going to have to find two numbers this time that when they're multiplied, they give you 12, but when they are added, they give you a -8. So we're going to start off again, and I'm going to put x and x in those positions, and now I need to find factors of 12. Well, if I multiply something and I get a positive, but when I'm adding them I'm getting a negative, that should indicate to you that you're going to use some negative factors to get 12. And so what two negative numbers multiplied together give you 12? Well, -1 times a -12 would get you a positive 12. And then we have a -3 times a -4 also gets you that positive 12. And a -2 times a -6 would also give you 12. So there are negative factors this time that we need to use. And we move on to the next question, which is which one of these factors would give you a -8 when added, and hopefully you can pick this out right here. So if I took a -2 plus a -6, then you get a -8. So those are my factors I'm going to substitute in up here into my binomial. And again, I would check it, of course, and I always do a little quick mental check in my head. You don't have to be elaborate about it. And usually if you're going to get it wrong, it's your inner and outer terms that wouldn't work. But let's try it. We have x times x, that gives you x squared, -2x times plus a -6x, that gives you your -8x, and -2 times a -6 give you a positive 12. So my signs all work out, and therefore I must have the correct factors. Here's some guided practice problems for you. Try to factor them. It doesn't take long. Pause the video and come back and we'll compare. Okay, well here's what I got for answers. Check them with yours. And when I got to number 2, I was a little fooled. It took me a second, but I'm like, there aren't any factors here. But when you go back up and read the directions, it says if the expression cannot factor, say so. So number 2, you actually cannot factor. There are no two numbers that when multiplied give you a positive 9, but when added give you a -3. For number 1, you can remember do a quick check, and it's usually the inner and outer terms that would mess you up. So here I have a -6x for my inner terms plus a 3x for my outer terms. That is indeed a -3x. Make sure you have the negative sign with the 6. And some people wonder what if I had this whole binomial second, and what if I wrote x plus 3 and x minus 6. That is totally fine because it is commutative. You can change the order, but the key is that the negative sign or the minus sign is with the 6. Number 3, checking the inner and outer terms, positive 9r plus a -7r does indeed give you a positive 2r, so that's confirmed there. And then 9 times a -7 is a -63. Again, make sure that your plus sign is with the 9 and your negative sign or minus sign is with the 7. All right, in this next example, there are special products that sometimes happen when you're multiplying two binomials together. These are actually extremely important to the rest of your Algebra 2 term, so make sure that you really understand these and you're not just glossing over them because they can be a little disturbing. So let's look at these two special factoring patterns. The first pattern is called the difference of two squares patterns, and what that means is if you had these two original binomials, a plus b and a minus b, what happens is if you look at your inner and outer terms, you have a times b here, and you have a times negative b there, so that's a negative ab and a positive ab. Your middle term always goes away. So what happens is you end up getting a squares of the first term and squares of the last term. Now remember, a and b here are the same numbers. There's two of the same number, and b are two of the same number. Maybe it's easier to actually look at the example. So here I have a letter x, a variable in the first position, and there as well. So those are the same numbers, and you have the same numbers as your last terms. And the only difference is you have one that's being added and one that's being subtracted. And so what happens is when you FOIL this, your inner and outer terms will always obliterate each other and be gone. So you end up with just the first terms, which is x squared, and you end up with the last terms, which is 4. And so that will always be negative as well. So whenever you see an example where you have a perfect square in the first position and a perfect square in the last position with a subtraction sign in between, you know that this kind of situation was necessary in order to create that. And when we get to examples, perhaps you'll recognize it more. Then you have what's called your perfect square trinomial. What that means is you had some binomial and it was being squared. And perhaps you remember this expression is saying if you have a binomial and it's being squared, you square the first term and you square the last term and you double the product of the two terms. That means you take 3 and x and multiply them to get 3x, and you double that. So 2 times 3x gets you that 6x. And so when you see a trinomial coming out and you have a perfect square here and a perfect square there, you really need to consider that this is where it started from. That the square root of x squared was x and the square root of 9 is 3, and then you squared it in order to get that trinomial. It also works if you have a negative sign here. That just means you started with a I should call it a minus sign. If you had a minus sign here, it means you just had a minus sign in your binomial that you were squaring. And I know I went through that really fast, so feel free to rewind, but perhaps the next practice problems we do together will help you. Alright, well here's some examples, and I'll just tell you off the bat they are all special patterns, so you don't have to wonder about it right now. And so we will look at letter A to begin with. And the number one thing you need to realize is there is no middle term there. And so what I start to do when I see these is I know I had two binomials, and I know I had one with a plus sign and one with a minus sign. I also know that my letters or numbers in the first position had to be identical. That's how you got an m squared. So I would fill an m in there. And then you also had to know that your spaces in the last position were identical, because when you FOILed, you multiplied it by itself, and that would be 11. And so let's actually FOIL this for a check. I'll just write that we're checking it. And if I did m times m, I would get m squared. I do the outer terms, I get a negative 11m. I do my inner terms, I get a positive 11m. And I do my last terms, and I get a negative 121. And right here is the key to see, is that those inner and outer terms totally cancel each other, and that could only happen if you had this special pattern where you had the difference of squares, meaning you had binomials that were identical in everything, except one was a plus sign and one was a minus sign. Alright, moving on to B, I would notice that I have a trinomial, and so that's coming from a special pattern as well. And I can see that because I have a perfect square here in r squared, and I have a perfect square there of 7. And you should always double check it, but if I started off with r and I put a plus 7 here and another r plus 7 there, which is the square root of 49, I'll write it better in a minute, but I just want to show you this, is that you have r times r, which is r squared, and then you had 7r for your inner term, and you had 7r for your outer terms. Well, that's where that 14 is coming from. And finally, you had 7 times 7, which got you 49. And so what you would do then, you wouldn't finish here, you would clean it up, and you would say, well, that's the same thing as writing this binomial to the power of 2. All right, we'll look at letter C again. These are definitely harder to see when you have the perfect square trinomial. And here I have a perfect square, p squared, and there's a perfect square, 144. Now, it's not always guaranteed that this number came from that, but it's pretty good indication, and you should always check that this pattern is taking place. So I start with my two binomials. I have a p here and I have a p there. Now the difference is I have a minus sign in front of my 24, so that's pretty much telling you you had a minus sign in both of these binomials. And then you take the square root of 144 and you get 12. And my next step right away is to confirm that my inner and outer terms, when added, would give me this negative 24, and they do. Negative 12p plus a negative 12p is that negative 24p. And so I just do that quick check before I assume that this is this special pattern. And so then I write it compactly as p minus 2, that binomial squared. You do guided practice 4 through 7. Pause the video and come back. Okay, well, here are the answers we get. The important thing to notice again with number 4 and number 5 is there are no middle terms. So your binomials, numbers, and letters had to be the same, except you had one negative or subtraction and you had one addition. So there's a subtraction addition. Again, it doesn't matter where you put the subtraction and the addition sign as long as there's one of each. Number 6 and 7 are also those special binomials called the perfect square trinomials. This was a perfect square, that was a perfect square. I could write them as this binomial squared. And remember, this from Algebra 1 is when we saw something like this, we would say you square the first term, you square the last term, and you double the product of the two terms. So I took 8 times y and got 8y, and then if I doubled this product, I would get 16y. And that doubling of the product comes from the fact that this is y plus 8 and y plus 8. You're doubling it because you have two factors of 8y. If that makes sense, great. If not, don't worry about it. With more practice, you will be okay. Okay, well, that was actually all just a review of some concepts in Algebra 1, and now we're ready to move on to the purpose of the lesson, which was to actually solve a quadratic equation and find out what those x values were. So let's remember that a quadratic equation is written in standard form like this, ax squared plus bx plus c. The difference now is we have not seen this before. We're going to set it equal to 0. Normally we've had it set equal to just y. Well, this is a special one where we can actually find out what x is as long as it's set equal to 0. And it brings up a new vocabulary word, which is the word roots. And it sounds really tricky, but it's not. All it means is the solutions of a quadratic. And again, it's really meaning what does x equal? Quadratic. Sorry, tick. There we go. All right, and we need to go back to our zero product property, which you've been learning about, I swear to God, since like 2nd grade, right? And it was the zero product property says if a product of two expressions is 0, one or both of the expressions must have been 0. How else can you get 0? So let's write that down. And here it is written. If the product of two expressions is 0, one or both of the expressions must have been 0. There's no other way to get 0 as a product. In algebra, we can write like a times b equals 0. Well, if that equals 0, then a must have been 0 or b must have been 0, which is very intuitive to us at this point. But what we haven't been used to seeing is binomials written like this, but they are factors. So if I had x plus 5, this binomial, times that binomial, guess what that means? It means this whole binomial must have been 0, or this whole binomial must have been 0. And so what we're going to do in this lesson then is we're going to break that apart and say, well, this first binomial must have been 0, or this binomial must have been 0. And these whole things, when they're written together with parentheses, are called factors. So this is a whole factor and that's a whole factor, just like A was a factor and B was a factor. So get used to seeing two terms being used as factors and being set equal to 0. So looking at example 3, they're asking us to find the roots of this equation. In other words, they're asking us to solve this quadratic. Well, it is a trinomial, and we need to factor it first. We need to break it up into its two parts that when multiplied got you this trinomial. And so we are going to factor, and remember I said you always start with your two binomials. In this case though, we're going to set them equal to 0, and we know that if we got an x squared there, that we must have had an x here and an x there. And now we're saying to ourselves, what two numbers, when multiplied, got us a negative 42, but when added, got us a negative 1? Well, you go through your list of possibilities, and you should see that you end up with a negative 7 times a positive 6 would get you that negative 4. And we'll put those in, negative 7 and a positive 6. Now, the important thing here now is to see that I have this factor being multiplied by that factor, and they're equaling 0. So at this point we can break it up and say to whoever that x minus 7 had to be 0 in order to get 0 for a product, or x minus 6 had to be 0. Sorry, x plus 6 had to be 0 in order to get that product. And now you're just solving two equations separately. And I would solve the equation on the left for x by adding 7 to both sides, and I would multiply or solve the equation on the right by subtracting 6 from both sides. And so these turn out to be your roots or your solutions of this quadratic. X is either 7 or x is a negative 6. And if you plugged either of those back in, you would see that one or both of them work. Here's another problem that we can practice, and it's x squared minus 5x minus 36 equals x. Remember, your first step is to factor this trinomial into the two binomials that created it when they were multiplied. You look at your first term x squared and realize that the first term of each binomial had to be x in order to get it. Then you say to yourself, which two factors when multiplied give me a negative 36, but when added give me a negative 5? And if you think long enough, and sometimes it takes a while, you will come up with negative 9 and positive 4. So there are my two factors that now equal 0. And we can solve them or find the roots by setting each one of these factors equal to 0, because one of them had to be 0. How many times can I say that to you? I don't know. So now I'm going to add 9 to both sides and see that x had to equal 9 or x had to equal a negative 4. These are my roots or solutions to that quadratic, meaning what values could x be. All right, this guided practice problem is wrong, so I'm going to give you a new one. And there it is, and I want you to factor that and then end up solving for x or finding the roots of that quadratic. Pause the video and come back when you're done. Well, remember, we write down our parentheses and get ready to fill in our binomials. What two factors of 6 when multiplied give me 6, but when added give me 5. And you should have come up with 2 and 3. And then you write this line out very formally. Do not skip any of these steps because you are building things that we're going to use in the future and end up solving here. So don't get lazy and skip steps. So x had to be a negative 3 or a negative 2. Now, we need to talk about another little bit of vocabulary, and that is called the zeros of a function. Zeros of a function are really the x-intercepts of a function, where they cross the x-axis. We call them the zeros of the function because your y value had to be 0 in order to land on your x-axis. So if I had a 0 of a function here and 0 there, and I'll say this was the point 4, 0, and I'll say this was the point negative 3, 0, notice that your y values were 0 each time. So what you're really finding here when you're looking for the solutions or the roots of a function, you're really finding the x-intercepts where your parabola crossed that x-axis. And that is why up here you will notice that instead of y, we're putting 0. We're really finding the x-intercepts. This is all kind of different language, very subtly different, but it all kind of means the same thing. So the function's values is 0. The function's value is 0. when you have found the intercepts. And so we call these things also the zeros of a function. You can call it the solutions of a function, you can call it the roots of a function, but you can also call them the zeros of the function for this reason. So in this next example, you'll see them wording it differently, but they're really asking you the same thing. They're going to say find the zeros of a function by rewriting the function in intercept form. Well, what's intercept form? Recall that intercept form was y equals x minus p times x minus q. Well, look at it closer. These are just two binomials, so it looks like a trinomial that's been factored already. So go up to this example and it says y equals x squared minus x minus 12. Well, I'll write that down, I guess, again. I don't know why. X squared minus x minus 12. And now instead of putting a y there, if I'm being asked to find the zeros of the function, you know that to find the x-intercepts, y had to be 0. So instead of writing y, we're going to write 0, and then I'm going to factor this trinomial. And the factors will be x plus 3 and x minus 4. And so now you should notice that it is in intercept form. And so when you solve this for x, you're going to get that x equals a negative 3 or x equaled a positive 4. And really that's coming right from picking out the p's and q's. And so we would write our intercept as negative 3, 0 and 4, 0. That's a bad looking 4. 4, 0. And so now you've just written them as intercepts or zeros instead. Same idea, though, they're also the solutions of the quadratic. All right, letter B, I'll walk through it one more time. We have y equals x squared plus 12x plus 36. We are being asked to write it in intercept form. So we are going to replace the y with a 0, and we are going to break up that trinomial into the two binomial factors that created it. And so I'll put my x in my first position, say what two numbers multiplied give me 36, but when added give me 12. Well, that's 6 and 6, so this really was a perfect square trinomial. But I'll leave it in that form for now. But if you would set it up and solve it, if you wanted to break it into its two forms, you could say x plus 6 equals 0 or x plus 6 equals 0. You're certainly welcome to do that. Or you could have noticed that these were your p's and your q's, and both p and q would be a negative 6. Well, that's what you get when you solve this. So hopefully you can kind of see this is your same process for all three of these last types of problems. So x equals negative 6 are actually the zeros of my function. They're the intercepts of my function. They are the solutions to my function, and they are the roots to my function. So all that vocabulary just for kind of doing the same thing. All right, guided practice, it's your turn. They're asking you to find the zeros of the function by rewriting it in intercept form. So get started with that, pause it, and come on back. All right, well, here are your answers, and I'd like you to notice how I wrote them. And I only wrote them all differently to kind of show you what answers I would accept. If they're asking you to find the zeros of a function by writing them intercept form, I'm fine with you giving me the answers for x as intercepts in that notation. I'm so fine with that. Or if you just wanted to say, for example, like x equals negative 3 or x equals 10, you have still found me the zeros. Those are still the intercepts and the solutions. And then this one was a perfect square trinomial, and you end up with one example again. And I will show you very soon in the future what these look like graphed and why sometimes we get one answer or sometimes we get two. Think about that.